Let's define position, displacement, average velocity, instantaneous velocity, average acceleration, and instantaneous acceleration vectors in terms of our handy unit vectors, I hat, j hat, k hat, for some object moving in 2 or 3 dimensions. Here we've got a 2D example. Here's an overhead view, a map of some object moving in the xy plane, and in black is the path the object takes through that plane over time. So at some particular time, say t1, if the object is located here, then we can indicate its position at that moment by this red position vector, r. Throughout what follows, I'll use red to indicate all vector quantities and blue to indicate all scalar quantities. So why the letter r to indicate position? Well, it's because we're thinking of this picture. If you're located here at this particular time, then your position vector is like the radius of the circle you happen to be sitting on at that time. So r is for radius. Okay, so here's your position at time 1. And as you move along this path, your speed could be changing. So you might be going rapidly through the first part and then slowly around this curve here and then speeding up again. So your position is a function of time, and your velocity is going to be a function of time as well. The components of your position vector are your x and y coordinates. And so those will be functions of time as well. So let's define your position vector. R as a function of time will equal your x coordinate times I hat plus your y coordinate times j hat plus your z coordinate times k hat if you happen to be moving in the z direction as well. So each of your 3 coordinates are the scalar components of your position vector, and those scalar components are functions of time. We say the path is parameterized by time. Time is the parameter. By picking a specific value of time, it tells you where you are on that path. So here's our position vector at time 1. Let's draw in the position vector at some other time. Say when you're located here. Let's say at time 2, the object is at this point. Okay, here is our position vector at time 2. So that'll be r at time 2. Oh, I need some more colors. Let's stick with our red for vectors and blue for scalars. You can be drawing all of this. I'm drawing this picture while I catch up to my own thoughts here. There we go. Okay, position at time 2. Okay, then, if you're located here at time 1, and then sometime later, time 2, you're located here, then clearly you have some displacement. There's a difference between your final position and your initial position. So let's define displacement now. Your displacement vector, delta r, well, delta is always a change. That'll be your final position minus your initial position. So your position at time 2 minus your position at time 1. Now, these are vectors, so we need to take this vector minus that vector, r at t2 minus r at t1. Okay, we know how to subtract vectors one from the other because we've discussed how in unit vector notation we add vectors component-wise. So you would sum up the x components, the I hat terms, sum up the y components, the j hat terms, and so on. So if we want r at t2 minus r at t1, we're going to take the x components at time 2 minus the x components at time 1. And let's introduce some shorthand here to save on writing. Let's suppose x at t2, we can just write that as x sub 2, and y at t1 would be y sub 1, etc. So x at time 2 minus x at time 1, the difference between those would be the I hat component, or the x component of our displacement vector. Likewise, y at time 2 minus y at time 1, so this coordinate at time 2 minus this coordinate at time 1 would give us the j hat component of our displacement vector. Likewise for z. So for short, we see that the components of your displacement vector are equal to the displacement in x, the displacement in y, and the displacement in z. If we want to visualize what that looks like, let's do it first with the parallelogram method. R2 minus R1, this vector minus that vector. That means the same thing as R2 plus the opposite of R1. So if we want to use the parallelogram method to visualize the new vector, we'll put R2 and minus R1, or the opposite of R1, tail to tail. So that's R1, R at time 1. So the opposite of R1 would be that vector flipped, reversed in direction. So this is the opposite of R1 there. So put them tail to tail like such, and then we'll need, then we'll need to complete the parallelogram that starts with these two sides. So let's see. I'll need a side parallel to R1 and a side parallel to R2. There's our parallelogram. And the sum of these two things, R2 plus the opposite of R1, or in other words, R2 minus R1, can be found by drawing in a vector that points from this corner to the opposite corner. So our displacement vector, delta R, must look like that. There is delta R over the time interval t1 to t2, pointing down and to the right like that. So it looks like on this picture, our displacement vector kind of points like that, as if it's pointing from the position at time 1 to the position at time 2. That's exactly what it does. We have another method, though, to find to sum vectors. Let's look at the head-to-tail method instead. Delta R, our displacement vector, is R2 minus R1. If I take this equation and add R1 to both sides, it looks like this. R2 equals R1 plus delta R. So it's like we start at R1 and we add some change to it to get our final position. So written like this, I can find this final position vector, R2, by taking R1 and adding the delta R to it. So in the head-to-tail method, we can start with R1 and then put the tail of delta R, tail of this, at the head of R1, so make that chain. And the sum points from the very beginning of the chain, the tail of R1, to the very end of the chain, the head of delta R. So that then would indicate the sum of those two vectors. That indicates R2 right there. So we've kind of gotten these pictures to agree with each other. And what they're showing is that our displacement vector between time 1 and time 2 points from your position at time 1 to your position at time 2. So that there is our delta R vector, our displacement vector. Okay, so if we've got our displacement vector, the next thing we can use that to define is our average velocity. Okay, we have an earlier definition for average velocity. In 1D, it just looks like this, your delta x over delta t. And our definition here is very similar, except since we're in more than one dimension now, we need our vectors. So instead of your single delta x here as your displacement, we have your delta r, your vector displacement, divided by delta t. That's going to define our average velocity vector over some particular time interval, from time 1 to time 2. Now, we're dividing delta r by delta t, which would be time 2 minus time 1, our change in time. But that delta t, that's just a scalar. So I could rewrite this as 1 over delta t times delta r. And we recognize that what we're doing here is taking a vector, delta r, our displacement vector, that's this vector right here. We're taking that vector and multiplying it by a scalar. The reciprocal of delta t, that's just a scalar, that's just a number that's going to rescale this vector delta r. That tells us that our average velocity between time 1 and time 2 is a vector pointing in the same direction as our displacement vector from time 1 to time 2. So our average velocity vector is parallel to that delta r. So there is our v average during that time interval. So no matter what you did between this time and this time, your average velocity during that whole time is a vector pointing from where you started towards where you ended. Let's finish working out the components of that. So I'm going to take the components of delta r, the displacement, and multiply each component by 1 over delta t, this scalar here. So these are the components. Let's see. These are the components of delta r. So I'm going to multiply each one of those by 1 over delta t. So the components of our average velocity will be delta x over delta t, delta y over delta t, and delta z over delta t. So we can express our average velocity vector in this form. So the x component of average velocity is delta x over delta t, the y component of average velocity is delta y over delta t, and the z component of the average velocity is delta z over delta t. Okay, let's pause there.